Hello, this is our financial literacy for students video presentation. The goal we aimed to tackle was that of students lacking any access to structured financial knowledge. For this, we implemented a financial search engine that bridges the gap between financial illiteracy and financial literacy. We hope that a project like this would help students understand real-world financial situations that they will inevitably encounter in their professional careers. Our dataset statistics were gathered using a combination of the Pandas library and our custom-built data processing class. With these two methods, we found an average document length to be roughly 64 tokens, an average query length of roughly 6 tokens, and an average relevant documents per query of 10 documents. We process our text in a 4-stage pipeline. We begin by normalizing the text using the lower function and some rechecks functions. These functions make all text lowercase, strips all punctuation, and collapses all contiguous white space. After normalization, we tokenize the text into discrete vocabulary tokens across the white space using the split function. After tokenization, we remove common words using Scikit-learn's English stop words list. Finally, we strip suffixes to root form using NLTK's order stemmer.
Hi guys, I am Arpit. Now I will cover the next few slides. So after the cleaning the text, we need to organize it so we can search fast. We build an index and just think of it like the index at the back of the textbook. Instead of reading every page to find a word, you just look it up in the back and you can find where the word is and where is the chapter is. So we built two types of indexes. The first one is a CSR matrix and the second one is the SMAP. So a matrix for our vector space model, this is called CSR matrix. So it stores how important each word is in each document. And then the SMAP for our other models. So basically like a dictionary where you look up a word instantly and it tells you when and which document have it, like where is the word is occurred in which document. And we also had 4 ways to score how relevant a document is. The TF-IDF, BM25, BIM, which is a binary, and the language model. I will cover those in the next slide. So here are the 4 models which we have done. So how we do actually decide which document is most relevant. So these are the 4 models. VSM, BM25, binary independence, and the language model. So VSM, imagine every document is an arrow in a space or in a graph. Your query is also an arrow, one of them. The smaller the angle between them, the more similar they are. That's the cosine similarity, which is mostly using in the vector space model. Then the BM25, this is like a smart librarian. It considered not just if a word is appear or not, but how often it will be appear in the document and also adjust for the document length in this model. So a long document doesn't get unfair advantage just because it has a more words. So it will be like a fair enough for all the documents. And then the binary independence, BIM, the simplest one. It just asks is this word is in the document or not. Just answer that yes or no, like a checklist. And then the language model. This asks if this document wrote your query or not. How likely is that? Like a probability based, and the handles rare words using smoothing, so nothing gets a 0 score. That's the language model. And then just a quick look at the mathematics of the models. So the first one is the BIM score and the language model, which we have used in our models. So BIM formula, it gives each word a weight based on how rare it is across all the documents. So rare words that appear in the documents are more valuable. Think of it like this. If everyone owns a pen in a class and finding a pen in someone's bag tells you nothing. But if you find the rare book, which is condensed by 10 people, and your suspect has it, then that's the clue about it, that your suspect is one of them. And then the language model. So it mixes two things, how often the word appears in the document and how common it is in overall in the collection. The lambda 0.3 value is for a smoothing, like it controls the balance, and it will put, if there is any value towards 0, then it will be smoothing with the 0.3 and it will be not become the 0 at all. That's the reason of the smoothing. And then the log space. So multiplying tiny probabilities like a 0.01, 0.02, 0.03 causes the computer to round down to a 0. Using logs turns multiplication into the addition. It gives us the same result and without rounding errors. So it is better to use in values like a 0.01, 0.02. So we can round up it. And then our system architecture, how we worked overall stack here in our project. So it is a full picture of how everything connects. So data comes in as a JSON and get cleaned through our pipeline. Then it is indexed and then searched by 4 retrieval models. And results shown in a Streamlit web app which is a Python library, same as like a Flask. So for the tools, we use the Python for everything, Pandas to handle the data, NLTK and the Scikit-learn for the text processing, and rank BM25 for a BM25 model, and Streamlit for a UI. In Docker to package it all of, so it runs in the same on any machine, like putting our whole project in a box that anyone can open. That's it. Thank you.
Okay, so as we discussed during class presentation, now we are going to see result analysis, precision decay across top 10 results. So what is P at K? So precision at K measures what fraction of the top K written results are actually relevant. We can see graph of average precision at K and rank position. As you can see, BM25 is performing better compared to others, while BIM and Bigram LM is performing bad. Takeaways are PM25 dominates graceful decay, VSM surges at K equal to 2, and BIM plateaus. Next, we are going to see result analysis. 11-point precision recall curve. So, the PR curve, precision recall curve, shows the trade off between finding more relevant docs and staying accurate. We have graph of interpolated precision and recall. Again, we can see BM25 is performing better compared to BIM and Bigram LM. We have BM25 P at 0 equal to 0.76, Unigram LM at 0.71, VSM at 0.67, BIM at zero point 0.5, and Bigram LM at 0.51. Next, we can see every query ID with the graph of average precision AP. So there is the result analysis per query performance across models. Once again, we can see BM25 is performing better, and it peaks at AP average precision equal to 1, while BIM Bigram LM is performing worse. So for query 2376, it peaks at AP equal to 1. We can see high variance across queries. BM25 is generally on top, while BIM is constantly low. So next we are gonna see all the key takeaways. BM25 is clear winner here. We compared few models like BSM, BM25, BIM, Unigram, and Bigram LM. We saw the full NLP pipeline. It is mathematically rigorous, and Bigram LM underperformed here. Thank you.
Here is how we implemented the search engines described in the presentation. First, we define a data processing class that does some global data processing. We define a tokenizer and use some service level normalization, remove punctuation, and provide a stemmer. This is done for all the queries and documents. For the data processing, we just open up the directories, and then we create some initial values to be calculated before the querying process, such as a TF-IDF vectorizer. For this example, we'll just go over the search engine that performed the best. Upon initializing this class, we call the tokenizer we described earlier along with the BM25 class, and we just do a simple query on the relevant documents to get only relevant documents to the query. Next, we just do some pre-computation, and then we go into the search where we are going to apply the query values with our pre-computed values. For our implementation, to keep it pretty simple, we just use the default values that the library provides, which means K1 equals 1.5 and then B equals 0.75. Just calculate those values, we sort them, and then package them up. And then after we do this initial search to get this ranked documents, we can then call the compute AP which gets the ranked values, the average position of the ranked values. And that's pretty much it. An example usage, we see that to get the ranked docs, we just call bm.search. You provide the queries, and then we just get the sort AP values, and then we can also, with those AP or the searched values, we can also get the MAP value. An example execution, you can see right here. And this will run BM25, VSM, and BIM. There we go. We have at the top, we have all the query IDs. For BM25, we have the AP values ranked from highest to lowest, with the highest being 2376 for this instance. We have the average MAP, and we did the same thing for VSM, BIM, and we also have the implementation for Unigram and Bigram, which are located here under the language model. The reason we implemented all of them was to compare each one of them with the queries to see in a practical sense how all of them would function. And now to look at the actual load time. When we first load up, the indexing process takes around 20 seconds to complete, but after the indexing process, the querying process is quite fast. Just give it a couple minutes. There we go. We can select any one of these search engines that we implemented, and then we can take a query that we have, press enter, and then we quickly get the AP score of the document.